The first part of the homework will ask you to implement an analytic solution for unoccluded area lighting. I did say in the Monte Carlo lecture that there are seldom analytic solutions. This is one exception that I think you should implement. It also provides a test case to check the correctness of your Monte Carlo renderer. We will consider lighting from a uniform polygonal area light source. We will consider integrating the projection of the polygon P onto the unit sphere. We assume uniform radiance incident from the light Li. We assume that there is no emission from the seen surfaces and no occlusion for now. There is an interesting construction which is known as Nusselt's analog, where you take the polygon, you project it onto the unit sphere, and then you project it again onto the unit circle. In fact, this is the same computation you did in order to compute the irradiance, and that is what we will be looking at. Note that this computation is valid only for a diffuse or Lambertian BRDF. If you have a non-Lambertian BRDF, you need to modulate by the BRDF. The equations we'll have are as follows. Here we have a simple equation. This is the direct lighting, and it's an integral of the incident light. Notice that since this is an area light source with a constant intensity, I just have Li. This f function corresponds to the BRDF. And here is the cosine term. Now in this case, the BRDF is Lambertian, so the BRDF is simply equal to Kd, which is the diffuse coefficient, divided by pi. Okay? And that corresponds to this Kd over pi. Recall that when I discussed irradiance, I said the maximum value for a Lambertian BRDF is 1 over pi. So Kd is the diffuse albedo, and it is in the range of 0 to 1. Li is a constant, so I can pull it out of the integral, and so for Lambertian BRDFs, I just have this cosine term inside the integral. There is interestingly an analytic formula for the irradiance. It goes back more than 30 years to work by Baum and this beautiful paper by Arvo on analytic irradiance tensors. It's useful to get a precise answer and check the Monte Carlo calculations. Arvo defines something known as an irradiance vector. I'll go over it slowly. We can have this diagram, which is from Arvo's paper. You have a polygon. You are projecting it onto the surface of the sphere. Within the sphere, you have this spherical polygon that is traced out. He's, of course, drawn it a lot better than what I can do with the pen. You define this angle between Vk and Vk plus 1 on the spherical polygon, which is essentially the angle Vk r Vk plus 1. And that will correspond to this quantity theta k or theta I, which is shown here. Similarly, you can define the quantity gamma that is shown here. And gamma is an interesting quantity that corresponds to the normals with respect to the cone formed by this vertex and the polygon. In effect, one is finding normals like this to the cone. This is actually going out of the plane of the paper. Similarly, normals here. We can look at the specific details here. The thetas are the angles subtended by the n edges of the polygon as seen from R. In fact, given the vertices of the polygon in cyclic order, that means that it's mod of n. If you have n vertices, the n plus 1 vertex will go back to 0. or to 1 rather, since you're starting from 1. Gamma 1 through gamma n are the unit normals of the polygonal cone with cross-section P and apex at R. In fact, the formulae are as shown here. So you have simple formulae to compute theta k, which is simply using the vertices vk minus r, the vector from the center of the sphere to weak polygon location vk. The center of the sphere is just the spatial location that you are shading. Similarly for vk plus 1, and you take the inverse cosine. So essentially you're computing a dot product of the unit vectors to find the angle, and then you take the inverse cosine. For gamma k, similarly, you're finding the normal to the cone, and that is done using a cross product. For the simplicity of your implementation, the formulae are explicitly listed on the slides and in the homework assignment. Then there is a simple formula for the irradiance which modulates by the intensity of the light source, takes the irradiance vector, and does a dot product with the surface normal. That is the formula shown here. Notice that the irradiance vector is actually more powerful and can be used for higher order tensors for non-diffuse reflection if you want to read Arvo's paper. Finally, for the direct lighting, you simply modulate the irradiance by the BRDF. That's a simple formula here. It's a general way in which you can get the reflection from diffuse surfaces. The BRDF for a Lambertian surface is simply the diffuse albedo divided by pi. And so we have our final result, which is kd by pi times the lighting intensity Li times the irradiance vector dot product with the surface normal. The assignment goes into somewhat more detail, but the slides have essentially given you a step-by-step way of how to solve the homework and the details of why you're doing it in this particular way. You will have to implement a new command in order to have an area light. We enable general parallelogram light sources as quad lights. You will give the origin of the parallelogram, the vertices corresponding to B, C, and D. In fact, what you will actually give is the vectors corresponding to AB and AC, and then the radiance of the parallelogram. You shoot your primary rays like a ray tracer to find all the geometric intersections in the scene. This assignment only affects the shading or the direct lighting at the relevant pixels. You use the analytic formula in the previous slide from the shading. And if you have multiple light sources in the scene, you simply add the contribution for all the lights. You will notice that we are not considering emission or visibility yet. That will come in the next part, which develops a general Monte Carlo numerical method. However, from doing this, you can create an image like this, and you will notice that unlike Monte Carlo rendering, this image actually has no noise because it is a purely analytic solution.